Hi guys, welcome to the lesson of partial differential equations. So in previous classes, we discussed about the homogeneous heat equation with some various types of boundary conditions. So now in this class, we are going to discuss the non-homogeneous heat equation with the boundary conditions, right? So the, the idea of non-homogeneous heat equation is that we have some function of x and t with the equation, right? So initially in previous cases of the homogeneous heat equation, we saw that there was no function of x and t present in the equation. So now we'll see that in the equations, the function of x, t will occur, right? So now we will see how to deal with these types of problems. So the first type is that if we have a function of x only, let's say that if we have function of x only like this, so what will be the approach to the problem, right? So here we uh, took an heat equation and these are the boundary conditions. So now we are concerned to see that how we can implement the solution to these problems, right? So the general idea is that we solve for the steady state and transient state temperatures in the case of non-homogeneous boundary conditions. So similarly, if a function of x only is present, so the method of solution will be same, right? So we will have two solutions, steady state and transient temperature, right? So now we know that for the steady state, the change in temperature with respect to time is zero. Therefore, the equation will reduce to this form. Now we can see that here the function g of x is also present. This is basically f of x, right? So this is f of x. So we are left with only this f of x and this c square u x x, where this is zero for a steady state, right? So now we can uh, write this function precisely. If this is a function of x only and this is a derivative of x, so we can write it as an ordinary differential equation. So it will be converted in this form: c square d square v over dx square plus gx, right? So now we know how to solve these types of equations. We can use the method of undetermined coefficients, or we can directly solve by integrating the equation, right? So this is a simple equation. So if you want to find v of x, so v of x will be equals to, we have to integrate this negative g of x divided by c square. We will integrate this function twice, right? So we will get v of x, and then the problem will be converted to the homogeneous equation, right, in this form. So then we can solve for the transient temperature. From this equation, we will get transient temperature, and from here we will get a steady state temperature, and then we will sum up for the particular solution, right? So now we'll take an example. Let's say that ut is equals to 1 over 4 uxx minus 1 over 4 sine of 2x, and the boundary conditions are given as mixed boundary conditions, right? So these are non-homogeneous mixed boundary conditions. And one of the initial condition is also given here, that is ux0 is equals to 2 sine 3x over 4 minus sine 7x over 4 minus 1 over 4 sine 2x, right? So now what we'll do, here we can see that the function, that is f of x, is equals to negative 1 over 4 sine 2x, right? So we will use the formula. Here we can see that this is the formula. Actually, I have to change this thing. Here it is f of x, so we should write f of x everywhere, right? So f of x, and this we will write as g of x. It doesn't matter whatever is f of x or g of x, it's just for understanding that you will have some function of x here, right? And here. So I'm just changing because I write there f of x. Therefore, I have to write everywhere f of x, right? So it will be f of x here, and then f of x here, right? So now we can see that we generated two equations. One of the equation is ordinary differential equation and one is partial differential equation. All right, so here we can see that this is a ordinary differential equation and this is partial differential equation, right? So the sum of the solutions will be the solution to the heat equation, will be the actual solution, right? So now here it will be g of x because the condition we write it as g of x, right? So now we can see that we can solve these two equations, and then on adding we will get the particular solution that is given by ux of t is equals to wx of xt plus v of x, right? So let's take an example. This is the example we started with. We are given with the heat equation that is non-homogeneous, and we can see that the function of x is present in the non-homogeneous part and the boundary conditions are given. These are the mixed boundary conditions. So now we can start solving the problem by dividing the problem into two parts. That is what we discussed, ODE and PDE. So ODE will be d square v over dx square is equals to minus f of x divided by c square. So c square is actually 1 over 4 that is given in the equation. So this is 1 over 4. All right. This is positive 1 over 4, not negative, right? So we can see here that this is c square, right? This is actually c square. So we can write 1 over 4 in place of c square, and we have a function of x as negative 1 over 4 sine 2x. So this 1 over 4 and 1 over 4 will cancel each other, and then minus minus plus, so we're left with sine 2x. Now this is our second order differential equation, right? So you know how to solve the second order differential equation. We can integrate this equation twice, so we will get v, right? So here is the first step, that we integrated this one time, then we again integrated the equation and we get the function of v in terms of x. Then to apply the boundary conditions, we know that the one of the boundary condition is normal boundary condition, that is Dirichlet, and second is the Neumann's boundary condition. Therefore, we need to calculate the derivative, but we already know that the first derivative is here, right? Here it's the first derivative. So we can apply the boundary conditions, given that v of 0 is equals to 0 and v prime of 2 pi is equals to negative half, right? So we will apply the first boundary condition, that is v of 0 is equals to 0. So we will get c2 is equals to 0. And then we will apply the second boundary condition, that is v prime of 2 pi is equals to negative half, right? So from here we will get c1 is equals to 0 as well. So now the function of x, that is vx, we will get as negative 1 over 4 sine 2x, right? So now we can use this function in the PDE that is now the homogeneous PDE, this one. We will solve this PDE, right? So now this PDE is the boundary conditions are homogeneous, the PDE is homogeneous, and we know how to solve the PDE for transient temperatures, right? Because this is now a homogeneous PDE with homogeneous boundary conditions. And for initial condition, we know that W of x comma 0 will be equals to f of x minus Vx, right? So f of x here is this function, this one, what we call g of x actually in the previous part. So it doesn't matter, as I told you, so we can write here g of x to avoid the confusion, right? So it's g of x minus v of x. So v of x we already calculated and g of x is given in the initial condition here. This is actually g of x, right? So now we can subtract v of x from g of x and we will get the initial condition for this problem, right? So this negative 1 over 4 sine 2x and negative 1 over 4 sine 2x, it will cancel each out. So we will left with only this function, right? Now we can solve the homogeneous PDE. And for case 1, we know that it will have a trivial solution. We already solved these in the previous lessons, right? So if you can remember, it's good. You don't need to solve. You can just write directly the answer that this case will give a trivial solution. And again, case 2 will also give a trivial solution. So we will left with case 3, right? So for case 3, that is lambda is equals to negative p square. We know that and the function of x will be a cos px plus b sine px. Here it is, right? And the function of t will be c to the power negative 1 over 4 p square t, right? This c is a constant. So don't be confused with it. This c is just a constant, right? So, so again, we are given with boundary conditions. So one of the boundary condition is w or t is equals to 0, and other boundary condition is the derivative boundary condition 2 pi comma t is equals to 0. So for this, we need to find the derivative of this function x is equal to a cos px b sine px. Therefore, we find the derivative and then we will apply the conditions. So this condition tells us that x of 0 is 0. Then this condition tells us that x prime of 2 pi is equals to 0, right? So we will apply the conditions respectively. So a will be equals to 0. And then for x prime 2 pi, we will have bp cos 2 pi p is equals to 0, right? So from here we can find p, and this is cos 2 pi p is equals to 0. Therefore 2 pi p is cos inverse 0. That is equals to 2n minus 1 pi over 2, right? So you can write here that cos inverse 0 is equals to 2n minus 1 pi over 2, right? Like this. So p is equals to 2n minus 1 over 4. Therefore, x is equals to b sine 2n minus 1 over 4x, right? And t is equals to c to the power negative 2n minus 1 whole square over 64 times t. Therefore, we will combine the solution because we know that w is equals to x times t. Therefore, we will take product of these two equations. That will be bn sine 2n minus 1 over 4x e to the power negative 2n minus 1 whole square over 64, right? So this is basically 64, and square is only on 2n minus 1, like this. All right. So Applying the, now we will apply the initial condition. So initial condition is wx comma 0 is equals to 2 sine 3x over 4 minus sine 7x over 4, right? So now we will apply the initial condition. Initial condition is equals to 2 sine 3x over 4 minus sine 7x over 4. And we know how to apply this condition to the problem, right? So wx comma 0 will be equals to summation n1 to infinity bn sine 2n minus 1 over 4x. That is equals to this function, right? So now we will generate the series to compare the coefficients, right? So the coefficient, this b2 will be compared with this, and then here somewhere b4, right? This b4 will be compared to this is 1 actually, right? And all other will be 0, coefficient will be 0, right? So here we write as b2 is equals to 2, b4 is equals to -1, and all other bn 0 for all bn not equals to 2, right? For all, we should write for all n not equals to 2, not bn, for all n not equals to 2 and 4, right? So therefore we will now generate the solution. So this is a transient temperature, but we know that we need both steady state and transient, right? So steady state temperature is already calculated. Transient state temperature is also calculated. So we can sum up these temperatures to find the general solution. And for particular solution, sorry. So this is the particular solution for this problem, right? This is the final answer for the given problem. Now we can discuss another question. So here you can see that the question is given ut minus uxx is equals to -4 over x. Then the boundary conditions are given. Ux of 0 comma t is equals to 4, ux of y comma t is equals to 8. And here we can see that initial condition is also given, right? So again, we will break the problem. Again, we know that the steady state temperature is where the temperature does not change with respect to time. So we will only left with this part, uxx is equals to -4 over pi. So when we say that this uxx will be equals to 4 over pi, therefore we can write it as v double prime is equals to 4 over pi, because function of x on the both sides, and this is independent of t, right? So we can solve this by integrating twice. We will get the function of the function v in terms of x, that is this function, right? And the problem will be converged to this PDE, and this will be now the homogeneous PDE, right? So then wx comma 0 is equals to f of x minus v of x. F of x is actually this one, this f of x is this, right? So because what we are doing actually is this wx comma 0 is equals to ux comma 0 minus v of x, right? So that's why we are calling it function of x only, because t is 0, right? So v prime is equals to 4 pi x plus 4 pi x plus c1, and v is equals to this. Now we will apply the boundary conditions. Boundary conditions are Neumann boundary conditions. So from here we will get c1 is equals to 4 and c1 is equals to 4 from both boundary conditions. So we do not get any value of c2. So we can say that c2 is any arbitrary constant, because we cannot get the value from the given boundary condition. So c2 may take any value, right? So we can take it as 0. It doesn't matter to the solution. So now v of x is equals to 2 over pi x squared plus 4x. And Now we are going to solve this PDE, right? That is the transient temperature for this problem. So now Wt minus Wxx is equals to 0. The problem is converted to homogeneous boundary conditions. The initial condition is also changed by doing f of x minus vx. So we are left with this function 6 plus cos 2x. And this is homogeneous equation with homogeneous Neumann boundary conditions, solved for 3 cases, right? So if you already know the solution from previous problems, so you don't need to solve again for 3 cases. You just can simply write that case A will give W of xt is equals to A naught, right? This is trivial because we know that for homogeneous Neumann boundary conditions, we have trivial solution for case 1 and case 3, that is for lambda is equals to 0 and lambda is less than 0, right? And for case 2, we know that it will be a non-trivial, sorry, this is non-trivial, not trivial. This is non-trivial. For case 2, it will be trivial, right? So we don't need this case 2. So now we'll solve for case 3, that is lambda is equals to negative p square. Again, now we are very much familiar with this process, how to make this process happen, right? So x is equals to a cos px, b sin px, t is equals to this function. X prime will be equals to negative ap sin px plus bp cos px. Therefore, x prime of 0 is equals to 0 plus bp. From here, we will get p is equals to 0. From here, x prime of pi, we will get the value of p because sine p pi will be equals to 0. Therefore, pi is equals to, p is equals to n pi, right? So, sorry, p will be equals to n because p pi will be equals to n pi. This is n pi, and this pi will cancel, and p is equals to n only. Therefore, we will plug the value of p in the equation. So we will get x is equals to a cos nx because b is 0. We already saw that by applying the boundary condition, and t is equals to d to the power negative n square t. And we can combine the solution here. Then we know that this AD can be written as a series, sum of a series or sum of a sequence, right? So wx comma t will be equals to summation n is equals to 1 to infinity a n cos nx e to the power negative n square t. So here we'll use the principle of superposition because we got two non-trivial solution, that is for case 1 and case 3. So this will be a naught plus all of this function. And therefore w of x comma 0 is equals to a naught plus this is equals to 6 plus cosine 2x. And from here we can just compare the solution. This a naught will be compared with this constant 6. Therefore we can say that a naught is equals to 6. And then this series will be a1 cos x plus a2 cos 2x plus a3 cos 3x. It will be equated with this, right? We are equating the similar terms. So from here we can see that we will only get the coefficient of a2, all other will be 0. That is not equals to 1, right? Therefore the solution will be w of x comma t is equals to 6 plus cosine 2x e to the power negative 4t. Then u of x comma t will be equals to sum of the two solutions, that is steady state and transient state. Therefore this will be the solution for the given heat equation, right? So in this way you can solve the non-homogeneous heat equation with the non-homogeneous or homogeneous boundary conditions. All right. So there is only a minor change. Otherwise, all things are almost similar, right? So now we'll discuss PDEs with time-dependent boundary conditions, right? What we discussed till now were all time-independent boundary conditions, but now we'll discuss time-dependent boundary conditions for non-homogeneous heat equation. So now we will discuss the time-dependent boundary conditions for non-homogeneous heat equation. So in this case, the boundary conditions will be the functions of time. Now, previously we deal with constants and the boundary condition, but now the conditions will be a function of time, right? So let's see. These are generally the cases that may appear in the boundary conditions. All right, you already know about this. So now let's see. So solution in this case is given by uxt is equals to wxt plus vxt. Now the change is that these both are the functions of x and t. Previously, v was only the function of x, but in this case, v is function of x and t. So both wxt and vxt will be the functions of x and t, right? So let's take an example and we'll see how to solve that. Here is the question that ut minus uxx is equals to cosine t minus x sine t. And the boundary conditions are given sine t and cos t. So we can see that these are the time-dependent boundary conditions as the functions of time are given here. All right, so the initial condition is function of x, right? So now in these problems, we cannot start with the steady state and the transient state because there will be no steady state temperature in this case, right? Or it just depends on the boundary conditions. It may be a steady state solution, but it depends on the boundary conditions, right? So we don't know either this problem has a steady state or not. So we cannot start by saying that we are finding the steady state temperature, right? So consider a solution Wx comma t that satisfies the boundary condition. Wxt is equals to C1x plus g of t, right? So this solution will, we will find the solution of this equation and we'll see that this will satisfy the boundary conditions and the problem, right? So now W of 0 comma t for this function. W of 0 comma t is C1 times 0 plus g of t is equals to sine t. Therefore, we get g of t is equals to sine t, right? And then Wx of pi comma t is equals to C1. That will be equals to cos t, because when we differentiate partially with respect to x, this g of t will vanish, right? So we will only left with C1. So C1 is equals to cos t because in the boundary condition we are given that u of pi comma t is equals to cos t. So C1 is cos t, therefore now we can describe the solution in this manner that w of xt is equals to x cosine t plus sine t, right? So now we can solve the partial differential equation, right? So the partial differential equation will become homogeneous. Again, we can solve it like as we solve for transient state solution. So in the similar manner, we solve it. Now this is homogeneous, so we can solve it easily by separation of variables, right? So boundary condition Rv of 0 comma t is equals to 0, Vx of pi comma t is equals to 0, and then initial condition will be v of x comma 0 is equals to u of x comma 0 minus w of x comma 0. Therefore, this is given as 2x, and this we found as negative x cos t, sorry, positive x cos t plus sine t, right? So we will plug 0 here for t because the initial condition says that t is equals to 0, right? So this will be 0, and here we will get x. So 2x minus x will be x. So this is the initial condition. And we know that for this condition, we will only have the solution for case 3. That is lambda is equals to negative p square. And applying this lambda is equals to negative p square, we get the function of x and the function of t respectively, right, in this manner. And then we will apply the boundary conditions from the equation that are x of 0 is equals to 0 and x prime of pi is also equals to 0, right? So therefore x of 0 is equals to a is equals to 0, right? Because when we apply 0 here, so it will be a cosine 0 plus b sine 0. So sine 0 is 0, therefore we will be left with a, because cosine 0 is 1, so a is equals to 0. And then x prime of pi, we will find the derivative. The derivative will be bp cos px, then we will substitute pi in x, so we'll get bp cos p pi is equals to 0. Then cos p pi is equals to 0 implies that p is equals to cos inverse 0 over pi. Therefore, cos inverse 0 is again 2n minus 1 pi over 2. Therefore, this pi and pi will cancel each other, so we're left with 2n minus 1 over 2, right? So now we can write the function of x and t by substituting the value of p. Therefore, now this is the solution. V of xt is equals to this function, right? This is the general solution, but still we need to apply the initial condition to find the particular solution for this w of xt, v of xt, sorry. Therefore, x is equals to bn sine 2n minus 1 over 2x. So this is a Fourier series, Fourier sine series. All right, and we know how to solve Fourier sine series, right? So this is a half range series. Therefore, we will apply the half range series formula, right? So bn is equals to 2 over pi 0 to pi x sine 2n minus 1 over 2x dx. So we will integrate this using the by part rule. Negative x times cosine 2n minus 1 over 2x over 2n minus 1 over 2 and sine 2n minus 1 times x over 2 divided by 2n minus 1 over 2 whole square, and limits are from 0 to pi. We will apply the limits. Here we can see that 2 over pi is equals to negative pi times cosine 2n minus 1 over 2 pi. It's 0. We already shown this in the previous step. So this cosine 2n minus 1 over 2 pi is equals to 0, right? Because you know that cos inverse 0 is equals to this term, so cos of this will be equals to 0. And then sine 2n minus 1 over 2 pi over 2n minus 1 over 2 whole squared, plus then we will plug 0 here. This is negative x, so it will be 0 times this function, so it will be 0, and sine 0 is also 0. So we will only left with this element, right? So this is equals to negative 1 to the power n. So we can substitute negative 1 to the power n for this element, and here we did that, right? So this is the final form for bn. This is actually bn. All right, so now we can plug in bn in the equation of v of xt. So here we did that. Therefore, now u of xt is equals to w of xt plus v of xt, right? W of xt is x cosine t plus sine t, and v of xt is this function. Therefore, the particular solution will be this whole function. All right. So this is the answer, and we can verify this answer to the equation that was initially given. We can find ux. This will be our ux. And then we find u double x. So this will be u double x. And then we will find ut. So this is the ut. for this function and minus this, right? So when we will apply ut minus uxx, so these two will cancel out, this one and this one, because they are similar. All right, so they will cancel each other, and we will left with ut is equals to negative x sine t plus cosine t, right? And which was actually the case. We can see in the initial equation. Here we can see that it is given cosine t minus x sine t, right? ut minus uxx. So we are done. We have verified the equation, and we can also verify the boundary conditions. Here in this equation, we can see that this solution, we can see that if we apply u of 0 comma t, so this will be 0, and this will also be 0 because of sine 0. Therefore, we will left with x uh, cosine, this is u of 0 comma t, therefore this will be 0, right? Because here we will apply x, so it will be 0, and we will get only sine t. This will be also 0 because of sine 0, right? So u of 0 comma t will be equals to sine t. And then we know that ux of pi comma 0 is equals to, is given as we can see the boundary condition above. So here is the boundary condition, ux of pi comma t is equal to cos t. Therefore, ux of pi comma t, it's not 0, sorry, it's t, is cos t. So we'll differentiate this function with respect to x. So now here we will left with cos t, right? Here we will left with cos t. This will be 0. And when we will differentiate this, this will be cosine 2n minus 1 over 2, right? This one times x. So when we will apply the pi here for ux of pi comma t, this will be cosine 2n minus 1 over 2 pi, that is 0. So this will again 0, and we will only left with cos t. Therefore, this condition is also verified, right? And now we can also verify the initial condition, that was u of x comma 0 is equals to 2x. X comma 0 is equals to 2x, right? So when we will put 0 here in the equation, what we will get? We will get this x cosine 0. That means we will left with only x. This will be 0. And again, when we will apply t is equals to 0 here, this will become 1. So we will left with only this part, right? So this part is actually the sine series of x, right? So we can write x in place of this, because this is actually the sine series of x. We already generated the sine series of x, so we can write x. So x plus x, this is again x, so x plus x is 2x. So this condition is also verified. So it means that we are done and the solution is correct. We verified the equation, we verified the conditions, therefore this is done. So example, it's a special case of non-homogeneous Neumann boundary conditions. So I want to discuss this also. So now the equation is given that ut is equals to c square uxx, and ux of 0 comma t is equals to a, and ux of l comma t is equals to b. and this is the initial condition, right? So in this case, we discussed in the lesson of Neumann boundary conditions that we cannot get a solution if A is not equals to B, right? By using the formal way, that was by using the solution for a steady state and the transient state. But now in this case, we will get solution like this, that u of xt will be equals to w of xt plus v of xt, right? So v of xt in this case will be equals to b minus a over 2l x square plus ax plus c square b minus a over l times t, right? So this will be the form of the solution. So whatever the boundary conditions are given, we can use the boundary conditions to construct this solution, this one, right? So we can easily find this solution. And then the PDE will be converted to homogeneous form, this form, right? And we can solve it easily. So in this manner, we can solve the problem for the special case of Neumann boundary condition when A is not equals to B. That means that boundary conditions are not equal, right? So, and we know that when we will solve this equation, we will get the cosine series, right? So cosine series, and we can apply the initial condition to find these constants A naught and AN. Then we can generate the particular solution of this form, right? So you can take an example to solve these problems and in the similar manner in this applying this method, and you will get the solution, right? So it's all for the time being. Hope you guys will get some fruitful lesson and you'll understand this, right? Thank you.